Hi everyone. In this video, I wanted to show you a new method that I added to topologicpy. It's called pyvis, and it uses the pyvis Python library and JavaScript library. So I will show you the documentation for it. You can go to this one, pyvis.readthedocs.io, and you can read more about this amazing library. So in this tutorial, I wanted to show you how we can get a graph like this to be displayed from a topologic graph from a building. And this building looks like this. It's a cell complex. And you can also filter and kind of isolate some vertices. It's very interactive, so it's really nice. And you can, of course, move these things around as you wish. So let's get started. This is the tutorial. Sorry, this tutorial is going to be done in Jupyter Notebook. So we are going to start a new notebook here. And it's a bit involved, so we were going to take it step by step, and hopefully you can follow along. So the first cell that I'm going to type in here, you don't need to type if you have pip installed the latest version of topologicpy. We are now at version 0.4.37 or 37, as you know, as of this recording, but obviously it might we might publish new versions in the future. So because this is a development machine, I need to point it to where topologicpy is saved. So I will add it to the system path. So I will append C users CMJ documents / GitHub. As I said, you do not need these two lines, but I do need them on this machine. Okay, so the first step is to import all the classes and methods that we need. So there's going to be 1, 2, 3, 4, 5, 6 of those. So go ahead and type those as I am doing. From topologicpy dot cell import cell. From topologicpy dot cell complex. Be careful with the uppercase, lowercase. Import cell complex. From topologicpy dot topology import topology. From topologicpy dot graph import graph. And from topologicpy dot dictionary import dictionary. And from topologicpy dot plotly import plotly. Now, this new method, which is called pyvis graph, is actually included in the graph class. So if you go to the API documentation, here we go to topologicpy, and you go to graph, and you look under P, you'll notice a new method called pyvis graph, and we'll try to explain some of these things. These are very similar to the parameters that are used for plotly. So I try to make them as consistent as possible. So if you have used plotly with topologicpy to kind of color code vertices, this is very similar and should be familiar. Okay, great. So we'll run this one. Okay, that has run correctly. So the next thing is to actually create the geometry. Now, obviously, you could have the geometry already saved as an OBJ file or a brep file, and you just import it here. I don't have a building ready to go, so I'm going to make this kind of building that I showed you, which is this one. I'm going to make it from scratch, just using kind of function calls here or method calls. So I'm going to call it P, and it's going to be we're going to start with a cell complex, and we're going to start with a prism, a simple box. And these are not real sizes or anything like this. So the width is going to be 2. The number of sides on the x-axis is going to be 5. The number of sides on the y-axis are going to be 3, and the number of sides on the z-axis, like almost like floors, is going to be 4. And the placement of this cube is going to be at the bottom. So the center of it at the bottom face will be at 0, 0, 0. So it's just a box that is segmented, already has interior faces. And we are going to do a prism that is almost like a central kind of atrium that's going to be imposed on it. So C is equal to cell.prism. So this is just a single box or a single cell. The width of this is 0.8. The length is 0.8. The height is 1.2. So it's a bit higher than the building. And the placement is also at the bottom. Okay, great. So that's the prism. So now we will impose this cell on the cell complex. So the resulting cell complex, or P, is equal to topology.impose P again, and what is being imposed is C. So C is imposed on P. Excuse me. So now we're going to do another cell prism. So cell.prism, and this one has a width of 0.8, but a length of 1.4, so it protrudes a little bit. Same height equals 1.2, placement equals bottom, and this one will be merged rather than imposed. So same as before, topology P is equal to topology.merge, and we are going to merge P and C again. So I'm just reusing the variable names. All right, so let's see the result of these operations. So topology.show P, and hit shift return or shift enter in order to see it in line. We'll give it just a second because it's doing all these Boolean operations, and here it is. Okay, so that is our building. It already is segmented into, spaces on the inside. Now, in order for us just to see it a little bit more clearly, to kind of show the hierarchy of it, I'm going to make a cluster out of it, and I'm going to explode it. So explosion meaning that I will separate the cells so that it looks nice and I can understand it a little bit. So cluster is equal to, and let me maybe zoom in a little bit here so that you can see it. So cluster is equal to topology.explode P, and maybe we'll put a scale on that. So let's put a scale equals 1.5. We just increase the explosion, and then topology.show cluster. But in this case, I'm going to set the face opacity to 1 so that it renders as an opaque object so that you can see it better. All right. So just to repeat, we use topology.explode on P on this cell complex, and we gave it a scale of 1.5 in order to separate the cells a bit more. And then we are just showing this cluster with a face opacity of 1 being fully opaque. So shift return again. And we wait for it. Here we go. My computer is a bit slow today. But these are the cells, as you can see. So quite hierarchical, really good combination of smaller cells and bigger ones, more connected ones and less connected ones, which should give us a nice graph at the end. Excellent. So let's move on to the next step. Now, the next step is a little bit more involved, more difficult. So let's take it slowly and see how it goes. So what I would like to do is create nodes for the different types of faces and cells that we have. So the cells will get a node, each cell will get a node. But for the faces, as you can see here, we have kind of external vertical faces. We have internal faces that can be either external or horizontal, like walls or slabs. And we have kind of roofs, which are like top horizontal faces, and floors at the bottom here, which are the bottom faces or bottom horizontal faces. So there is a call in topologicpy called cellComplex.decompose, which is really powerful, and it gives you or it categorizes all the faces into their type, whether they are external or internal, whether they are vertical or horizontal, etc. So let's start by calling that, and that gives us a dictionary, a Python dictionary, where the keys are the types of faces and the values are the list of faces. So you get the topologic faces stored in that dictionary. So we're going to say D is equal to cellComplex.decompose, and we're decomposing P. And that's all you need to do. If you want to learn about decompose, again, just go to the API and go to cellComplex right here and look up decompose, and you can see what it tells you. And it also gives you the kind of the names of the types of faces that it will save. So all of these things will be in a dictionary, as I said. So going back here, this decompose will decompose, because it is a cell complex, it has decomposed the faces of the cell complex. So we need to add to this the cells. So I'm just going to add another key. So D cells, I'm going to call it. And I'm going to store in it the cells of the cell complex. So topology.cells P. Okay. So in addition to all the external vertical faces and horizontal faces, etc., I'm also adding another category, which is the cells, so that when I get my graph, it has everything is categorized correctly. Great. So now I'm going to get the keys of this dictionary. So the keys, as I said, are these labels that I showed you in the documentation. And in this case, it will have one more key, which is called cells, because we just added it right now. So dictionary.keys D. Now, you will notice that if we go back to the documentation, there are keys like bottom horizontal apertures, top horizontal apertures, external inclined apertures, all of these things. There's also external inclined faces. We don't have any topologies for those. These are empty. So we are trying to get the kind of smallest list of keys that do have topologies associated with them, and we want to get rid of the ones that don't have any topologies, simply because then the color coding will be nicer rather than having spaces kind of all colored similarly because they are in one area of the color spectrum, because there are a lot of these things that don't have any faces associated with them. I want to get rid of those and just simply come up with the smallest set of keys possible. So how do I do this? So I'm going to loop through the keys. So for key in keys, and what I'm going to do here, I'm going to say, okay, give me the topologies that are at that key. So dictionary square bracket key, external faces, internal faces, cells, etc. Now, I will create a list before I do this. So I'm going to go back up here to line 3 and insert a new line and just simply add a new empty list called vertex groups. And if you know Plotly, you know that vertex groups are what determines the colors of vertices later on. So this vertex group is going to be this kind of condensed list of only the keys that have topologies in them. So if the length of topologies is greater than 0, then vertex groups dot append key. So add the key only if it has topologies associated with it. So this new vertex group is the new kind of condensed list. Okay. Now we are going to define a function that assigns a dictionary to these faces, because they don't have dictionaries at this point, that tells topologic what they are. So we are going to define a function called assign dictionary. And this is going to take a list of topologies and a vertex group. And it will just assign that vertex group to those topologies. So we'll do a loop. So in this case, we're going to use the enumerate method from Python. So enumerate for IT, enumerate topologies. So basically, when you use enumerate, I will be the index, will be a number going from 0 to the length of topologies, and T will be the actual topology, will be the actual element in that list of topologies. So it's a nice way to get both at the same time, an index as well as the element itself. So we are going to create a new dictionary. So D is equal to dictionary by keys values. And what are we going to do? We're going to have one key called ID and one key called group. So those are the keys. These have to be matched by values. So one is going to be the vertex group plus the string of I. So the vertex group will be something like cells. So it will be like cells 1, cells 2, cells 3, or it will be external faces. So it will be, or external vertical faces. It'll be external vertical faces 1, 2, 3, etc. So we are going to use that for the ID, and the group is just the vertex group itself. Okay. So that is coming in, the vertex group is coming in from here. Great. And then we assign this dictionary to the topology T. So T is equal to topology.set dictionary, T again, and the dictionary is D. All right. So this small function here takes a list of topologies of a certain group and assigns the correct dictionary to it. And by doing that, when we derive the graph, the topologic graph, the nodes in the graph will automatically inherit that dictionary from the topology that they are representing. So the vertices will inherit the dictionary of the element that they are representing. Great. So now we need to call this function for all the topologies that we have. So for vertex group in vertex groups, you remember vertex groups is that condensed list of vertex groups that we have, like cells, external faces, internal faces, etc. We get the topologies of that group. So topologies is equal to D vertex group. Okay, so we look at the dictionary, we get the topologies that are at that vertex group, and we assign dictionary those topologies and that vertex group. All right. So as I said, this is a bit involved, but I hope you understand at least the concept of it. Is that I'm first of all condensing the actual keys into only the ones that have topologies in them and getting rid of the ones that don't, and then looping through this condensed list, and then getting the topologies of that list and assigning a correct dictionary for it, for those topologies. So basically, I'm creating a dictionary here. This is arbitrary. You can do it as you wish, but I'm doing two keys. One is called ID, one is called group, and I'm using the vertex group plus the string of the kind of number in it in order to give it a unique number, and the group of it is what group it belongs to, which is the vertex group. And this is coming from here. Great. So Shift Enter to run this. Yeah, I forgot the word in. So for IT in enumerate topologies. Here we go. Now this ran correctly. So now moving on to the next step, which is to create a graph. So G is our graph, is equal to graph by topology. The topology is P. We would like to have lines going to the external topologies. So that's equals to true. And we also would like lines or nodes at the shared topologies via shared topology. So all the internal faces that are shared between cells. So that will also get a node. And that is it. So this is graph by topology. Okay, so now let's draw this graph. So we're gonna get the Plotly data for it, and we're gonna also get the Plotly data for this building here, and we'll draw them together so that you can see what it looks like. So data 01 is equal to Plotly data by graph, and the graph is G. The vertex group key, this will determine the key in the dictionary to use for coloring the vertices. And this is, we called it group. So we're going to use it here. And what else do we need here? Vertex label key. These are all optional, really. Label key. Also, we can use the group key in order to get that. And we need to tell it the vertex groups that we have created. So this is also called vertex groups. And the color scale, finally, this is kind of a Plotly color scale. We'll just use thermal to draw it. Okay, so now this is getting too long, so let me just put a return here so that you can see it a little bit better. So this is data 01. Again, if you're not sure about data by graph, again, take a look at the documentation for Plotly, and you can see here data by graph, and you can read what these things mean. There are a lot of options here, obviously. Right, so this is for the graph. Let's do one for the actual cell complex, and that should be simpler to do because we're just going to draw the outline of it. So we're going to say Plotly data by topology in this case, and the topology is P, and the face opacity, just so that we can see the graph, we're going to set it to 0. So we're just drawing the kind of edges. All right, so these are the two data for Plotly. So now let's create a Plotly figure. So fig is equal to Plotly figure by data, and you give it data 01, and you put the plus sign, and then data 02, because these are two lists. So you just add them up into one big list. So that is the figure, and then Plotly dot show the figure. Okay. Right. So let's shift enter on this. Oh, okay. Two external topologies. I misspelled it somehow. Oh, not to external, sorry, to exterior. I always make that mistake. To exterior topologies. Okay. Shift enter. It'll take a while because there's a lot of data here. Oh, Plotly, I misspelled Plotly. Okay. So Plotly. What Plotly like this? One more time. Here we go. So as you can see, nicely organized, color-coded. There is a central cell here. These things would be top horizontal faces. These things would be external vertical faces. And you can see that when I hover over them, it doesn't always work very well, but mostly Plotly would work. It will give you the label, and then in parentheses, it will give you the group. So, and this is using the thermal color scale. All right, so the idea here now is, okay, we have this graph. It's not interactive, it is static, and I can't move the nodes. I cannot filter them. Plotly is not giving me, I could have done legends and stuff like that. But pyvis looked much nicer, and it gives you a flat graph like in 2D, so you can analyze it a little bit better. So the idea now is to take this graph and convert it into a pyvis graph. So that's just one call. So we'll just do this here. And this one, again, I've had some trouble with pyvis displaying the graph inside Jupyter Notebook. There's a lot of discussion online about people having trouble with that. I couldn't get it to work. The only way I got it to work is to send it to a new tab or to new browser window. And it seemed to work well that way. Your mileage may vary. If you are able to get it to work inline, please drop me a line and let me know how you did it. Okay, so let's do the call for the pyvis graph. This is called graph.pyvisgraph. It doesn't return anything, it returns none. But it will display it when you hit Shift Enter. So what are we doing here? We are giving it the graph. Then we need, excuse me, we need to give it a path. So I'm gonna save, because it saves an HTML file, is what it's going to do. So I'm gonna give it a path called Sinjay Notebooks, and I'm gonna call it pyvisgraph.html. Okay, and then comes the options. So I'm going to hit return and start typing the options. First, the background color for the graph is going to be white, comma, hit return. The font color is going to be black. The vertex label key, again, as I said, this is very similar to Plotly. We're going to use group. So it's going to look at the key called group. It's going to look at the value found there, and it's going to use that to label every vertex. And the vertex color, this is a default color. I'm just going to make it black, but we will use vertex groups in order to color code them. So this is just a precaution. And the vertex group key, this is the important one. Again, it's called group. So it will use those that key and the value at that key in order to determine the color to use. And we need to give it the vertex groups in order for it to find that value inside the list. So that is also called vertex groups, as if you remember from before. And the default vertex size is equal to, I don't know, 0. That's okay. The vertex size is going to come from how well connected the vertex is. So this is now what we are specifying, the vertex size key. Oops, let's make sure this is correct. Let me scroll down a bit so you can see it. So the vertex size key, again, very much like the vertex group key that determines the color, this is a key that will determine the size of the vertex, the size of the node. And if you put in a special keyword, which is called degree, a vertex degree is the number of connections it will look at the number of connections it has, excuse me, and it will decide on the size of the vertex based on the number of connections. So vertices that have more connections will be larger. So we're just going to use the degree as the vertex size key. And then the vertex color key, this is if you have specified an actual color inside the dictionary, but in this case, we don't have a vertex color. And then the edge weight key. I mean, a lot of these things can be left to be defaulted, but it's good to see them here. We're not going to use edge weights. You could draw some edges thicker than the other ones, and you can use a special keyword again here called length or distance. Both will work. That will draw longer lines in a kind of a thicker width. So this is none here. Notebook is equal to false. As I said, I'm not able to get it to display in a notebook mode, so I'm setting that to false. And then finally, the color scale. Oh, color scale is lowercase. Color scale, we're going to use thermal again. Okay, great. So there are probably, I think this is everything, but there, if you might go again to the documentation, take a look at graph, take a look at pyvis graph, and check all of these things. They're fairly well explained what they are, and you can follow those documentation. Okay, so let's go ahead and shift enter. And as you see, it will open up a new window, and it will take just a little time to load the graph because there are a lot of nodes in it. But as you can see here, I already have the selection menu and the filter menu because those are the defaults that it shows them. At the bottom, there will be also all sorts of settings you can change, but you can also leave those as they are. Okay, so here it is. This is the full graph. As you can see, there is one big central node here, which is this big atrium in the middle. And if you zoom in, you see the labels. And of course, we can move them around, etc. And if you hover over these things, it tells you what are the neighbors. So these are all listed in there. See here, this one has just 2 neighbors. And you can also filter. So if we want to see nodes that have a label, which is either cells or let's say external vertical faces only, just these 2, you click filter and you get just what you have asked for. So just cells, which are yellow, and these external faces, which is this kind of dark color here. And then you can reset the selection and again say, I'd like to see node that has a label of cells and internal vertical faces, and filter that way. So you can see now you get the cells with the internal vertical faces. And there's other options. You can, for example, filter on edge, and you can say, from, and you can say all the edges from cell ID 19, if you know what that is. And there it is here. So this should be probably 19. Yep, that's 19. And all the nodes that are connected to it. And then you can reset the selection to see the full graph. That's it from me. I hope you enjoyed this tutorial, and I will hopefully see you at the next video. Bye for now.